Thank you all for dialing into this unconventional, non-sponsor-esque discussion today. My name is Rob Bewick, and I lead Golder's global strategy on deep and mass mining. Golder is proud to be a sponsor of the 8th International Conference on Mass Mining, which is an essential forum for the interaction of great minds that would normally not connect under these circumstances. It is these interactions that spur creative thought and innovation in the industry. Our world is facing complex challenges that call for innovative solutions that push the boundaries of scientific discovery and deliver essential services to people around the world. Mass mining is one of those complex challenges and is an essential part of the supply chain for meeting society's drive towards electrification and more sustainable energy production. Today, we're going to look back on the progression of rock engineering and how engineers, in their quest to make mines more productive, drove change through innovation. This innovation has not been constant. There have been periods of step change with the advent of numerical modeling capabilities that were developed from nuclear weapons research in the 1940s. And there have been periods of consolidation, like we've seen over the last decades from around 2000 to now, where work has focused on progressive utility and efficiency gains from past step change. Today, we want to first look back on Golder's own experience of the developments in rock engineering that were driven by mechanization, numerical modeling code development, and the need for rock mass characterization. Secondly, looking forward, we now see rock engineering ready for its own step change, and we'll highlight some trends we see coming in the next 5 to 10 years, which in our view will be quite disruptive. Looking back at the trends that drove earlier innovation, Richard Beddoes, a principal with Golder who leads our technical communities and innovation program, will have a conversation with Ross Hammett, who started his career at Golder in the early 70s and was part of a leading group of rock engineering innovators. We'll then go back to the future to conclude our talk. And now, Richard, over to you.
Thank you, Rob. I've been working with Ross since the 1980s, and I joined him at Golder several years later, partly because of that sense of constantly pushing the envelope that was present in the group at the time. Ross is a principal at Golder, and over the years has driven many of our initiatives, including deep mining, blast monitoring, and paste backfill. In this conversation, we'll look at a few of the trends that have created innovation in the 70s and 80s, and highlight a few of the things that we were able to observe firsthand that shaped rock engineering today. So, innovation, we can see that as the result of recently available technology being adapted to meet a newly perceived need. And recognizing how this happened in the past, I think can give us a guide to recognize the opportunities that we have today. Ross, looking back at the developments in rock engineering over your career, we identified a few factors that encouraged periods of rapid innovation. One of those was mechanization. Can you talk for a minute about some of your thoughts on why mechanization was so significant?
Yeah, I got involved in mining in sort of the late 60s, early 70s, and at that time, one of the big discussion points on any new mine or developments within a mine underground, and this discussion is all on underground, was whether this would be a trackless operation or a conversion to a trackless operation, or whether it be mechanized. And that was quite a common phrasing almost. And of course, the answer to the question was yes, it will be mechanized. And so this meant that large equipment could now go underground. And so LHDs were developed, bigger jumbos, drilling rigs, trucks to transport the ore. And this led then to bigger excavations and a whole focus in the mining industry on efficiencies. Now, with bigger excavations, they have to be supported, or there was a lot of pressure on the rock engineering people who were coming through to maintain safe conditions and stability of these much larger excavations. So that was really a significant starting point on innovation from then on.
Yeah, so you picked on large excavations there, which were made possible and in some ways were required for the mechanization. So what sort of challenges did those present for the rock engineers at the time, and what was the response from those practitioners to those challenges?
Well, a lot of the support prior to that in these tract mines was, passive support, timber and things like that was the typical support. And by going for larger excavations, it wasn't really practical to continue that style of mining. So there was a implementation then of a different approach, which was rock bolts and mesh and shotcrete. The civil engineering industry had pioneered some of that somewhat earlier in the 1950s into the 60s. Much more extensive use of rock bolts or development of rock bolts in the excavations that they created, and they moved away from even large excavations that were quite more like crusher stations and things like that for underground caverns for power stations. They went away from concrete arches, support and things like that into straight getting the rock to, or helping the rock be self-supporting in itself, and so rock bolts, and eventually that led to cable bolts. But the civil engineering Snowy Mountains Authority in Australia pioneered a lot. I know Churchill Falls Power Station in Canada also was quite prominent in terms of this type of support. Drakensberg, which was much weaker rock in South Africa that Golders was quite involved in, that was all done with rock bolt and type support.
Yeah, so you particularly mentioned cable bolts there, and I know we've talked about the introduction of cable bolts in the past and the significance of that. When did you first see cable bolts getting used, and what are some of your recollections about how they came to be a critical part of the rock engineering toolkit that we have today?
Yeah, the development of cable bolts was sort of, as I remember it, the mid-70s into the 80s. I know Broken Hill Mine in Australia did a lot of pioneering work on them. This was the introduction of 7-strand cables, much the same as what we see now, and grouted in place. Prior to that, in Canada, I believe there were attempts to use cables using hoist ropes, and they had grease in them and things like that, and they really didn't work very well. And so there was at least the discussion was that there was a delay in getting cables into Canada because of that experience. But once the way that they were installing them in Broken Hill in Australia and Mount Isa mines and places like that, then the effectiveness of them was quite well proven. Golders with Ken Matthews came from Mount Isa mines to Golders in the late 70s, and we did quite a bit of work for Brunswick Mining and Smelting. And at the time they had very wide, very good rock, but very wide, like 30, 40 meters wide cut and fill stopes, and very little support in them, but the potential for wedges to fail and things like that. So they introduced cable bolts there, and the cable bolts were quite long, vertical deposit. And so the cables were quite long, and then they just mine through them, and they'd take a cut and then cut off the cable and put a plate on it. So that was the early days in sort of the early 80s in Canada that really started to get involved in cable bolts. And from there on in Brunswick Mining and Smelting, they went on to long hole stoping very quickly because the rock was so good. And this is all part of that trend of mechanization and changing innovation. And so they used cable bolts in the back a lot. And also they looked into it for hanging wall support. They tried putting drifts in hanging walls. And then excavating drifts and then bringing cables or installing cables back to try and support the hanging wall itself, which didn't work very well because the rock would just strip off the cable without a plate on it or anything like that. So that was sort of an attempt to support the entire hanging wall, and instead they went away from that and instead on the overcuts for each stope for an advancing upward mining method, then they would support just the strip of rock and the overcut wall at that elevation, just to prevent any instability beneath that in the hanging wall would be arrested and wouldn't continue up by continuing to undercut the hanging wall. So those were some examples of the use of cable bolts in sort of the early 80s anyhow. And from then on, cable bolts started to be used all over the place. Okay.
Thanks. Let's just go on now to one of the other threads of innovation that we've talked about, which is numerical analysis. Numerical analysis seems in some ways like a recent development because the vendors have so rapidly expanded the number of users by focusing on user-friendly software and running that software on laptops that it's in fact, we see it around the office all the time today. It makes it seem like a relatively recent trend, but really that's not true at all. Talk for a moment about the innovations that you saw come together in the 60s and 70s that created the foundations for modern numerical analysis in rock engineering.
Yeah, well, the first trend was just the availability of computers, which my history goes back to the early 70s, and there was certainly computing power available then. You bought it from purchased it from various suppliers. Golders in Vancouver used Boeing Computer Services and CDC machines. But prior to that, they were mainly in universities and some research, or maybe even before that in government organisations. The availability of computers, they were a lot different. There were punch cards in those days to get programs into the computers. There were modems that hooked up to Boeing Computer Services in Seattle, but and they were very slow by today's standard, but were deemed to be very large and powerful at the time. So that was the first one, was just the availability of computing power, which wasn't the laptops as we know it today. The second trend was software. So sort of the early days was finite element was mainly discussed, and I know that finite element concepts and even coding of some description was being pioneered in the 1940s. Then sort of the early to mid 1960s, Zenkovich in the University of Swansea published a book, and it became linked more and more to analysing stresses around excavations and such. So that was sort of the first trend towards using it for the applications we know it today. In parallel with that, there were finite difference codes being developed. I think some of the early finite difference codes were developed by Lawrence Livermore Laboratories in the US as part of the development of nuclear. And those sort of technology translated over to Berkeley University. Dick Goodman was involved in some of that in finite element, but finite difference codes were being developed there as well. Then there was the commercial operations, Physics International and Science Application Incorporated had commercial finite difference codes, which happened to be, the precursor of the FLAC codes. They were very similar to that. It was they were dynamic type codes that were damped down to provide static solutions. Very similar to what is used today. There were some others that were developed. The University of Minnesota Golders got involved with the development of displacement discontinuity codes in the mid-70s. And these were three-dimensional codes. There were other three-dimensional codes, but a lot of them were used in those days just for very single excavations or just a few small excavations, so very local. Displacement discontinuity in 3 dimensions allowed at least a certain level. It was sort of deemed to be a bit crude in terms of the sophistication of the analysis, but by calibrating it with the performance of the underground excavation by observation, we were able to use displacement discontinuity, and it's still used to this day. So we're able to use that quite successfully. But at the same time as well, boundary element codes came into vogue. I was in Imperial College in the early 70s, and the boundary element codes and stresses around various shapes of excavations were possible. So that's a general trend, and all of that is the starting point now, or was then taken to the types of codes we use today. Are not much difference, and the types of analysis we do are not that much different, except they're much more powerful computers now, and progressively people were able to code more and more complex features into the models that are available.
So, as you're saying, the basic underlying formulations of these codes go back a long way, but lots of developments have taken place over the years since then. What have you found to be the most impactful advances in these tools and their contributions to rock engineering?
Well, first of all, their availability, which has some good points and bad points, and we can discuss those. The power of the computing systems themselves. And then the application, it does let us understand in a lot more detail what's going on if we observe things or predict things. So it's really trying to predict things and understand how we're predicting it or why we're predicting it. It's just getting a much better understanding of how stress is impacting rock, how the rock then deforms. And progressively more and more features were put into these models that allowed you to take into account faults and structures and other variable complex load deformation behaviours that allowed you to understand what was going on. So that's the positive part of it.
So yeah, you talk about that positive part being the ability to help us understand what's happening in the rock, not necessarily simulate what's happening in the rock. Can you talk a little bit more about the risks and the opportunities that have resulted from the broader and broader use of numerical models and the way that we rely on them today?
Yeah, well, the opportunities or what they provided really was exactly as you say, that improved understanding, availability of computer codes now is extremely good, and so in more complex problems we certainly can analyze increased complexities in them. As far as the risk goes, some of them it's very difficult at times for people now with the programs that are so freely available, and they're more or less canned programs, and a lot of people running them really do not have a intimate understanding of the of what's in those codes and how they work and whether it's working properly. So the risks are a little bit that people sort of take the output and say that must be the answer without having an intuitive way to understand whether what they've analysed is reasonable or it's really telling you the right thing, or somehow there's either errors crept in or people have thought that the code would work in one way and it really operates in another way. So and in the early days a lot of us developed codes ourselves, and we were forever interrogating the codes and getting output so we could understand the sequence of the analysis and what the analysis was telling us, and add on complexity. So we started from simple analyses and added on complexities so we understood what the impact of each one was. And that's harder to do now because there's not as much knowledge about the actual development of the codes, and the codes are so complex. But that's some of the risks that one takes.
Yeah, thanks. And I think one of those opportunities that we'll come back to a little later, probably, and talk to Rob about it, is the potential offered by the greater and greater computing power that there is in cloud computing for us to do true probabilistic analysis, and the ability both to have larger models, but and also have models that you can run thousands and thousands of times in different with different combinations of inputs to understand the sensitivities and the range of possibilities that might come out of our incomplete understanding of the rock mass. So we'll come back to that a little later. So the third thread of innovation that we've talked about, Ross, is the area of rock mass characterization, classification systems, and empirical design. The thinking in this area was probably triggered by a combination of trends, the mechanization and numerical analysis that we've talked about before, as well as the increased attention to safety. So let's talk a moment about how the classification systems, the efforts in characterization met a need for operating decisions around stability and the support of larger excavations.
Yeah, this started in the mid-60s or so, and sort of the mid-60s into the early 70s was sort of the initiation of it. It started off, and it's the rock mass classification, trying to get some way of describing the rock mass with almost a single parameter, but taking into account by rating them the various factors that influence how the rock behaves around an excavation. So it was purely just a way of trying to describe the rock mass and how it'll behave. So RQD was one of the earliest ones in 1964 or so, mid-60s, and it was a fairly simple way of getting some representation of the rock quality. Then Q and RMR came in the early to mid-70s as similar sorts of processes. They were extended then into, well, now that we have some way of describing the rock, can we use that to try and understand what the stability of an excavation is and what support requirements might be? So there was a collection of information. So they'd take the rock mass classification and then the performance of the excavation, what support went in to keep it stable, whether it was stable or not. And so it was a correlation exercise then. And these became design approaches. And the key was that if for a particular excavation in a particular rock, that you were comparing similar conditions in other excavations and performance with the rock that you're actually involved in and designing. So it's very empirical, very much a correlation process of past performance and how you can predict stability and estimate support requirements.
Yeah, and of course we've been living with those classification systems for the past coming up for 40 years, and yeah, I think we'll talk a little bit later about where we might be headed in the future. In the 1970s, the Canadian government began to see the need to better prepare the mining industry for deeper and more productive mining, and it funded a significant amount of research through CanMet. And of course, there was similar government focus in Australia and South Africa, and in the US, but mainly focused on coal. I remember this research helped create the foundation for understanding of mining in high-stress environments. Stability charts for large excavations were born out of that same period of government investment. You've mentioned earlier in our conversation that you were working with Ken Matthews at that time. How do you remember the the Matthews method came about?
Yeah, Ken joined Golders in the late 70s and into the early 80s, and was with Golders for quite a long period of time. And just after he arrived, he was able to get a contract with CanMet to look at, and it was very specific, to look at the empirical design of excavations stopes in particular, mining excavations, at 1,000 metres or deeper. So the nature of the contract was for Golders to contact many mines and ask them, what size stopes they used and what was the geological conditions of that, the geotechnical conditions, and whether it was stable or unstable, and whether there was support and things like that, the geometry of the excavation. So all that information was collected, and then I can remember it was a Monday afternoon, about 2 o'clock, I believe, and Ken Matthews and Everett Hook and Byron Stewart and Duncan Wiley and myself sat around a table, and we brainstormed of how to package this together into something useful. And we followed the general model that had been used for rock mass classification for support that we discussed just a minute ago. And came up with, the approach that's the Matthews method that's used to this day. I think that was the first application of the use of hydraulic radius. A couple of us were trained as civil engineers, and we knew a little bit about hydraulic flow in channels. And that was where the hydraulic radius concept was used, and we took that, and as I say, I think that was the first application of that. These classification systems have gone on to other applications of a similar nature, caving, mining, and so forth. There's a number of correlations, in effect, or predictive methods that use similar approaches. The Matthews method was one of the early ones that was really into the mining methods or mine design, particularly for big excavations or caving, as I mentioned.
So similar charts have been refined for over 30 years now, and more data has been added to them, and they still get regularly used. Do you think there's more work that is useful to do in this area that can add value, or do you think we've reached the end of this path and that we just keep using the empirical things that we've got, but develop new things to gradually replace them?
Yeah, I think they will progressively get replaced. I think, as a concept, I think it's diminishing returns to some degree. I think we should keep collecting information and plotting it and so forth. But I think as a concept, it probably is pretty much diminishing returns in terms of us taking it very much further. And I think other methods will take over progressively as we move forward. And maybe the part of the discussion coming up now will be to talk a little bit about some of those things that might sort of progressively take over from them. But
yeah,
I think, yep.
Good, good. And rock mass classification systems have also become a standard part of deriving parameters for input to numerical models. When did this start? Why did it start, do you think, and how have you seen that evolve over time?
Yeah, the point that I think really sort of started it off was that the numerical analysis, the ability to do numerical analysis and the amount of numerical analysis need parameters to go into those codes, into the calculations. And we had to find ways of sort of estimating, particularly rock mass strength and stiffness and things like that. And so the starting point to some degree with that was Everett Hook, and Everett worked for Golders for a long time. And in the early days, I worked quite closely with Everett, and it started off with him looking at intact strength for conventional unconfined compression strength tests, and looking at the behaviour of those unconfined and then confined, and he came up with envelopes that described the strength of the rock mass from that curvilinear strength envelopes, and then we needed to try and get to a stage of then predicting what the rock mass strength was as opposed to the intact strength. And so he latched on to RMR and became GSI as another format of that, in his way of basically trying to describe the rock mass in something that's relatively simple, but incorporates the factors that we know affect these things, and then using that to come up with rock mass strengths for various rock masses. But that was sort of, it started off, I know, in the very early days, particularly for rock masses. Intact strength was straightforward. You had numbers and you plod them up. But rock mass strength was more complex, and quite a bit was learnt from pillar behaviour in room and pillar mines, because that's a fairly fundamental stress condition. But it was more complex, and I know some of the early strengths that were estimated, or the way that it was being estimated, were too low, quite frankly. And I know at one stage I said, most of the mines I'm working on are going to fall down if the strength really is that. But it gravitated towards something that now is much more realistic in terms of the strength of the rock mass.
Okay, that's great. Thanks, Ross. That was an interesting conversation. I think we've pulled together a few threads there of industry context and periods of innovation in the 60s, 70s, 80s that I think have carried the engineering within our discipline forward over the last generation. And now I think we'll turn to talking about the current context in the industry and the technologies that are coming along and how they might trigger a new era of innovation in our disciplines. Well, thank you.
So I guess the question now is, will rock engineering progress through a step change or continue to consolidate for the next decade? In our view, there will be a disruptive step change. And while things look similar between 2010 and 2019, the progression of change in 2020 to 2029 will be drastically evident. The context of mining is changing. There are more ultra high capacity and capital investment mines with greater risk related to rock engineering and its impact on production reliability. The rapid digitization and simulation of the world that is already impacting equipment, material flows, and processing will eventually touch rock engineering. The main limitation for change right now in rock engineering is the data stream. There's still not enough data related to rock mass response to mining coming from the underground, but there are some mines getting close to reaching the required data flow. This can and will be solved with current sensor technology on the market. It's only a matter of time. There's already a massive increase in connected devices globally, which stood at around 30 billion today. With that rate increasing, or the increasing amount of connected devices at 127 per second, that's according to Cisco, which when you look at this 40-minute discussion we're having today, there's another 300,000 devices being developed and connected now on the market. New tech and sensors, data analytics, image recognition, and visualization will all help to move rock engineering into the connected virtual world in operating mines.
So, Rob, what do you think all of this means for the better investigation of new mines, the more reliable design of them, and even the efficient operation of existing mines?
So two of the main technologies that create the ability for change are the cloud computing access and capability, and secondly, machine learning algorithms and platforms. While current modeling codes are not fully optimized for the cloud computing efficiencies, they're in the process of being optimized, and new tools are being developed specifically to take advantage of the cloud that do not have the constraints of the old current tools. But the codes optimized for the cloud, as well as the current processing technology available, we could then take those models of today that take weeks to simulate or run, and we could commute those in a matter of hours or minutes. With the cloud storage and infinite virtual computers that are available for rent, in a single day, we could run hundreds of mine scale simulations, and a true reliability-based design could be developed due to probabilistic assessment of those simulation results. These results could then be fed into discrete event simulation tools, and the rock's response to mining can be used to efficiently and more realistically design, schedule, and plan a mine, adding immense value to stakeholders. Now, this is really the short-term life of conventional simulation in mining. with the data streams that are going to come from the mines, and as they are stored and analyzed, a full ground response to mining model could be developed in these data-rich environments. And if you couple that with machine learning, there's a real disruption to our conventional simulations that will occur because they'll largely become redundant in that space. A true digital twin of a mine will be common practice, and the twin will be updated in near real time at the mine and provide forecasts for mining challenges, evolving and resulting in better safety management, planning, scheduling of resources, and material supply chain. Some of our colleagues at Golder have already developed machine learning models for predicting mine behavior that outperform conventional tools. So this really isn't blue sky thinking, and this change is already coming in our industry, and it's going to be here faster than you think.
These are really interesting developments that you were mentioning there. Just at the end there, you were mentioning machine learning. Where else do you see machine learning and AI impacting rock engineering?
I see that largely coming around the data collection piece. So examples of this are core logging for both geotechnical data and geology data, as well as underground face mapping. Soon, conventional core logging will be gone and replaced with smaller initial algorithm training data sets for a rock mass, and then reliance on core photograph and scanning data for near continuous data extraction. Several companies have sprouted in the field over the last couple of years in this space. We all know ore body knowledge is absolutely critical for a project, as well as to de-risk a mine. So every borehole drilled will have fast, cheap, and full continuous data along it. And consulting firms like Golder really need to be ready for this change, since our revenue streams will be impacted if we're not ready and leading in this area. Similar image assessment on underground LiDAR, for example, photographs and other scanning type data will provide for a underground environment. This will change conventional classification and characterization at the mine. Tools will be used to relate the ground environment, mining, and rock mass response in near real time and provide forecasts, making the need for classification systems and conventional characterization after the project stage potentially not required. Even at the project stage in the next decade, once mines have enough data flow and correlations have been processed from common mine response machine learned models based on different, for example, ore body geometry or geology types or deposit types, mine simulation work may no longer require any of our conventional approaches. And this part may be the most uncomfortable for us in rock engineering, but it's really not outside the realistic realm of possibility. Linked to all this, there's the risk of going backwards in rock engineering. An experience transition is currently going on in our industry. The previous thought leaders and owners of history are completing their journeys. The systems developed for rock engineering in the past, which have had stated specific limitations of applicability, which were well known to those at the time of development, are now at risk of being used when they should not be. If we are not careful, the step change that we're about to take or that is currently happening may get stalled due to loss of our history. And that's really why these conversations like we're having today are so important. So as we advance through this next step change in innovation for rock engineering, let's take care and not forget the lessons of the past. Thank you, everyone, for listening.
Thank you, Rob and Ross. Good conversation. Thank you. Goodbye to, and thanks everyone for listening.